Hello and good morning. Today we are going to discuss about fluid statics. Fluid statics means it talks about the behavior of a fluid when there are no external forces or when there is only gravitational force. So if you could understand this, so what do I mean by fluid statics is, first of all, what do I mean by fluid is, so in terms of material, we know quite a little bit about different types of material, densities of the material, and the volume of a material, area, shape, all these things. But the nature of the material, when we talk about it, we fundamentally divide it into solid, liquid, gas. There is something that's called as plasma. When we talk about this liquid and gas, the combined term used to somewhat decipher the properties of the liquid and gas together is the fluid. So the fundamental difference between a solid and a fluid contains both liquid and a gas. So fundamental difference between a solid and a fluid is, solid has strong cohesive forces. Solid has strong cohesive forces. That means the force of attraction between two particular molecules or atoms inside a solid is quite strong. Whereas in liquid or fluid, it is quite weak. Particularly in gas, it is much weaker. In liquid, it is still there, but still it's weak. So, when we talk about a solid, it contains several layers of molecules. Each layer is holding the other layer, such that it does not move away from each other. If you try to pick up one layer, the other layer will also come with it. So we call it a rigid body in terms of Newton's laws of motion and all that. But if you take a liquid, if you scoop some part of the liquid, the bottom layer does not come along with it. So that means while you are taking it away, the force of attraction between the two layers is not quite strong enough. The force of attraction is not quite strong enough between the two layers. So we say that the attraction force or the cohesive force, this is a word used, cohesive force, inside a liquid or a fluid is not quite strong as that of a solid. So the first property of a fluid is the forces of attraction or the cohesive forces in between the fluid molecules is not strong enough. The cohesive forces are not strong enough. Now, one more thing. Why does it not, even though the cohesive forces are not strong enough, let us say you have a solid, you kept that in a container. Let's say you have a container of the shape like this. You kept one solid. If you keep a fluid here, suppose you have a inverted container and you remove this container inside which fluid was there. So initially when the container was removed, the fluid has this shape, which is similar to that of a solid. Why does the solid retain, but this fluid does not retain? So the fluid actually comes out and fills the container, if you could understand that. Why does it not retain and why does this retain? There is nothing which is disturbing it. There is nothing which is pushing it so that it will move. There is nothing which is scooping it up so that it is removed. But why does this fluid fill out the container whereas this solid does not fill out? The idea is the fluid molecules are not actually moving in one direction. They are not vibrating up and down. The fluid molecules are trying to move in all possible directions. The fluid molecules are trying to move in all possible directions. It is a quite random motion inside a fluid. It may look counterintuitive, but it actually is quite random. What do you mean by quite random? Suppose you take one part of the fluid here This part of the fluid does not actually move up or down, but it will actually move in all possible directions depending upon the time and what has happened to it. Now, let us say at an instant this is trying to move this way, little bit to the left. Now, at this instant, there is nothing which is stopping the fluid molecule from moving to the left. And the cohesive forces, when it is trying to come out, so let us say the fluid is like this initially, and this part of the fluid has come out, or just about to come out. So there is a cohesive force which is trying to pull the liquid back. When it is trying to move away, there is a cohesive force inside the liquid which is trying to pull it back. Now the cohesive force is not strong enough. That is the idea. The cohesive force is not strong enough, so this liquid will come out of the liquid or the fluid, and the volume will be spread out throughout the container, and it will be spread out like this, where here also it tries to move, but this wall is pushing it back. The wall of the container is pushing the liquid back such that it does not come out of the container. So the shape is retained because whenever you talk about the shape of the container, the liquid at the edge of the container is trying to move out, is trying to move in all directions. When it is trying to move out, the container is actually pushing it back and not allowing it to go outside. That is the reason why the liquid is spread. Otherwise, if you just pour a liquid on a flat surface, you could see it spreads as far as possible into a very, very thin layer. So the shape of the container is the shape of the liquid because the container is actually holding the liquid and resisting it to go outside. So the container is actually giving a force on the liquid. Now, how much force is it giving? How much force is a container giving? And how to understand this force by liquid? So this is something we're trying to understand in this chapter, where we're going to see what is the force applied by a liquid on a container and vice versa. What is the container, how much the container is applying a force on the liquid. Now, let us take a container like this. It's like a cube shape or cylindrical shape, both are okay. We are taking a cube or cuboid container. Now, the water is filled or the fluid is filled to an extent. When this fluid is filled, the weight of the fluid is acting downwards. The total weight of the fluid is acting downwards, and this region in the bottom is actually applying a force upwards on the liquid such that the weight of the liquid is balanced. Now, how to understand the force? Let us take one imaginary cylinder inside this, which is completely consisting of liquid. Now, this liquid, in the large scheme of things, is holding its weight. That means the external forces are holding the weight of the liquid. If you take that as a liquid, the external forces are holding the weight of the liquid. Now, how to understand the external forces and what is the net force on the body? Now, the first and foremost, how does the external force direction work? The external force direction works in a very simple way, where force is always perpendicular to the area. Force is always perpendicular to the area. Why do I say so? Because if you could think of an area like this, the normal force will be perpendicular to it, and the liquid is trying to go leftwards, then only it will stop. If it is going to go upwards for this particular area, it will not stop. It will not stop the liquid which is trying to go upwards, but it will only stop the liquid which is trying to go leftwards or perpendicular to the area. So it will only stop the velocity which is perpendicular to the area. So the force will be perpendicular to the area. It will not stop when the velocity is parallel to the area. So the net force is acting perpendicular to the area of the liquid. So the liquid area and the container area are same direction. The net force is acting perpendicular to the area of the liquid. Now, if you could take areas here, the area of the liquid will be at the bottom will be horizontal, and the side of the cylinder will be in the shape of a circle. Now, in the shape of a circle, when you take the shape of a circle like this, the forces will be acting like this, perpendicular to the circle. So this will be in radial direction of a circle. So the force is always perpendicular to the area. Now, when you talk about this, the force is always perpendicular to the area, and the net force is balancing the weight of the liquid / fluid. Now, let us say here force is F1, here force is F2. Now, why would I say that the force is uniform at a particular height? Let's say this height is H1 and this height is H2 from the top. Now, the idea is this. The layer which is at a distance H1 from the liquid height is holding the top of the liquid, which is from 0 to H1, it is holding that liquid. So the net force will be equal to the weight of the liquid above. So if you could take a small area like this force is actually holding the liquid in this small region. And this force is holding the liquid in this total region. F2 is holding the liquid here and F1 is holding the liquid here. So the net force in this horizontal line will be similar, and this force will be equal to the weight of the liquid. Weight of the liquid I can get as the volume into density of the liquid. Weight of the liquid can be measured as the volume into density. These forces along this horizontal line or in the circular line will not have any upward force. They will only be in a circular line and they will actually cancel out each other. So there won't be any movement in this direction or in this direction, but there will be only net force in the upward direction. So net force F1 downwards, F2 upwards. Let's say the area is A and the height is H2 minus H1, where initially it is H1 from the top and here it is H2. So the net force acting will be equal to F2 minus F1 upwards. Net force F2 minus F1 should be equal to the weight of the body which is acting downwards. The weight of the body or the weight of the liquid acting downwards is equal to density of the liquid, that is the rho of the liquid, times the volume of the liquid, this is the mass, into acceleration due to gravity, which is A. Force is equal to ma. The net force is balancing the gravitational acceleration. Now, when you talk about this F2 minus F1, if this area is A, F2 minus F1 is equal to rho into, I can write volume is area of the cylinder into height of the cylinder. Area of the cylinder is A and height will be H2 minus H1 into G. So I will get F2 minus F1 is equal to, by A is equal to rho into H2 minus H1 into G. If I take H2 minus H1 is some H, so I will get rho into H into G. Rho into H into G. Where F2 minus F1, if I take individually F2 by A minus F1 by A is equal to rho Hg. Now, here comes the important definition we are going to use, which is the pressure of a fluid. Pressure means force per unit area. Force per unit area. So, force per unit area is pressure. The units are newtons per meter square. So, Newton is for force, meter square is for area. So, F2 by 8 I will write as P2, which is the pressure, and here I write as P1, that is rho Hg. So, what we have is a new concept which is talking about the pressure of a liquid, which is force per unit area. Force per unit area. And this pressure is actually responsible for the weight of the liquid, which is rho into H into G into A. So P2 minus P1 or delta P is equal to rho into H into G. So the increase in pressure, as you go down you can see the weight is increasing, so the force will also increase. F2 should be more than F1. So the pressure F2 by A should be more than F1 by A. So the pressure P2 will be more than P1, and P2 minus P1 is rho Hg. So as you go down, the pressure actually increases. So this is quite useful in terms of pressure, because we are not going to deal with the total volume of the liquid all the time. So whenever you design something, you will design for a particular area. Suppose you design a ship in an ocean. You are not concerned about the length of the ocean, the total mass of the ocean. You are concerned about how much force will be acting for my area, not for the whole ocean. So that's the reason why we are going to use pressure. It can tell us what is the force acting on our particular area. So you take a particular area and put it in water or put it in a fluid. What is the force exerted by the fluid on the body? Will be easily understood by the pressure. Now, when it comes to pressure, pressure is acting because there is gravity. Quite simply put, if there is no gravity, there is no pressure. If a fluid is in, let's take ISS, the International Space Station, there is no pressure inside the fluid at all. There is an interesting experiment where they do not have what do you call glasses in International Space Station, or for the ready space or thing that is moving. Now that is because the fluid is not actually contained in the glass. There is something called a surface tension, which we are going to deal later, where the fluid becomes like a ball, and they just put a straw inside the ball and they suck it up, and the fluid just comes into the human. So rather than containing in it remaining in a container, it will not remain, but it will become small balls. That is because there is no pressure. There is no pressure which is that is acting due to the gravity. Pressure is actually acting due to the gravity. So there will be no pressure inside the fluid. So without gravity, you will not have any pressure. Now, when we talk about this pressure, the pressure is because of the gravity or gravitational force of Earth. Now, if you could zoom out a little bit into the whole dimension of Earth, there is atmosphere surrounding the Earth. This is not up to scale. The atmosphere will be very thin when compared to the radius of the Earth, for you to understand. So this atmosphere will be attracted towards the center of the earth. We read that about gravitation, where the net force will be towards the center of the earth. So based on the whatever the gravitational acceleration is at this point, the net force will be downwards. So the whole weight of this air column is balanced by the normal force. The whole force of this weight of this air column is balanced by this normal force. So the weight of the air column, is balanced by the force. There is no force upwards. The weight is balanced by the force here. So the force should be equal to the weight. The force per unit area will be equal to weight per unit area, that is the pressure. As the atmosphere is uniform, we say the weight per unit area is also uniform. It is uniformly spread. Nearly the pressure, atmospheric pressure will be nearly uniform. So average atmospheric pressure, there is something called as average atmospheric pressure. Average atmospheric pressure, which will be experienced by a body present on the surface. So right now we are on the surface. If you could imagine, there is an air column above us, a column of air above us which is actually pushing us. There is a column of air above us which is pushing us, and that pressure will be experienced by us. Now why don't we just go down because of the weight of it? That is because I told you again, the pressure will be acting perpendicular to the area. Now if you take the shape of the human or shape of an object like this, the pressure is acting here, the pressure is acting here, the pressure is acting here like this, and it will also be acting down. The pressure will be here and the pressure will be here also. Now if you take a human, the pressure is acting in on whole of the body where you are a closed volume, so the net force will be actually zero due to the atmospheric pressure. But our body is designed to work under atmospheric pressure. So we are not quite rigid in the sense that we are not quite sealed off from the atmosphere. So whenever we go to an other planet, we need to maintain a suit which has an atmospheric pressure of air inside. Otherwise what happens is, the sweat and the blood inside us will just rush out, because if there is vacuum outside, there is a pressure inside, the heart is pumping and there is a pressure. With that pressure, the fluid will come out of the small tiny holes. So we will not be actually able to live without a suit which is holding the fluid from not coming outside. So there is a pressure which is trying to expel it outward, and there is a pressure which is keeping it inwards. So if the outside balancing pressure is removed, then this will just expel outside. So you can understand this if you take a bottle, and this experiment all of you must have done. If you just suck the air out into yourself, you have created a low pressure. There is less weight, less molecules hitting. So the outside pressure is higher, so the bottle will crush inside, because the inside pressure is lower and the outside pressure is higher. So similarly, this atmospheric pressure is there completely around us, where the atmospheric pressure, if you take the uniform atmospheric pressure, this is due to the air column above us. What is the air column we are holding? Because of that, we have an atmospheric pressure. Now, as you go up into the air column, suppose you got to a height of the top of Mount Everest, which is the tallest mountain. So there, the height is less. The height is less of the air column which is present above. So the weight of this air column will also be less. As you go up, actually the density also decreases quite a lot. So the total weight also decreases quite a lot. So as the density and height decreases, the pressure drops. That is the reason why if you go higher and higher, the atmospheric pressure comes lower and lower. And you will not be able to breathe and take the air inside. We are not going to create such low pressure inside our body. We breathe because we create low pressure inside and the air rushes inside, and this fills the lungs. So when you are not able to create such low pressure, you have to expand your lungs to create low pressure. We are not able to expand it after a little bit, after a particular amount. Then you will be not able to retain or take that much oxygen as you require. because the pressure difference is quite less. And that's the reason why we are not going to be able to survive at very, very high altitudes. Now, as you go up, the atmospheric pressure actually drops. As you go upwards, the atmospheric pressure drops because the height of the air column is less. The height of the air column is less. Second one is the density is less. And third one is the gravity is also less. The acceleration due to gravity is also less. So the total weight will decrease. The acceleration due to gravity is less, the density is less, as well as the weight of the air column. So height of the air column is also less. So the total weight will decrease. The total weight by area is the pressure. So the pressure will decrease from the same area. So that is the reason why the atmospheric pressure drops as you go up. Now, when we talk about the pressure inside a fluid, this atmospheric pressure is also acting on the top of the fluid kept on the surface of the earth. So if you keep a surface of the earth, if you keep this fluid on the surface, there is an atmospheric pressure, let's say P0 or PATM. Atmospheric pressure, that is the weight of the air column above this per unit area. Weight of the air column above this per unit area. That pressure is acting. Other than that, the pressure of the fluid is also acting. That is the weight of the fluid per unit area, which is rho GH. This fluid weight will be, per unit area will be rho GH. Plus P0. Both will be acting on this. So P0 will be acting upwards. And this rho GH will be acting downwards. So the net force inside, or the net pressure inside, let's say this is A. We already discussed the pressure difference here, P2 minus P1. P2 is upwards. P1 is actually P0. P2 minus P1. P2 minus P1 is equal to rho GH, where rho is the density of the liquid. Here P1 is P0. So P2 minus P0 is equal to rho GH, and P2 is equal to P0 plus rho GH. This is the pressure of a liquid at a depth h inside. And similar to this, we are going to have several examples in which the container is actually having irregular shapes, or container is in different shapes like this. And we are going to have container when it is accelerating, container when it is rotating. That way we will discuss later. And how the pressure will vary at these situations, and how the force will be varying at these different situations. Okay, thank you.